गुड मॉर्निंग सर।
हाँ गुड मॉर्निंग। 1 मिनट रुको, शेयर करना है ना। Can you hear me?
यस
Hello.
सर। यस सर।
The screen is shared.
यस सर शायद।
So let me start. So let me start. Okay. Now we look at the previous node isometry. So whatever that I have taught, but I want to talk about equivalent matrix. So that is given in page 123 and 124. No, 120 to 123. So this is equivalent matrix. Okay, this is very important. In fact, I have done another equivalent matrix special, uniformly equivalent matrix. Now look, equivalent matrix, I have given a result first. The proof is very simple. Actually, equivalent matrix, usually people do it. Suppose you have on X, same set X, you have two matrices. Okay. And tau d, remember that tau d is the family of all open sets. कौन आज कर रहा है इतना? Open sets generated by D. Similarly, tau rho. So tau D and tau rho, it may be same. If it happens, then we say that they are equivalent metric. If this happens, look, it's not rare, it often happens, because if you take D, then if you take 2D, 2D means you just multiply by 2. So this will give you the same metric. Okay. In fact, you are just expanding the scale by 2, multiplying the scale by 2. So they will give you the same class of open sets. So they are equivalent. Here I said that this theorem, like I have given two more equivalent conditions, that it will be equivalent to take identity map xt y rho. So not only, look, this is apparently different metric. This will be continuous and inverse. Inverse is also identity map, but from different direction. This is also an identity map from here. This is also identity map. Since I am using I here, so I inverse. You can take I1, I2, but both are identity map. So they will be, both of them will be continuous. That means, look, here it is sending convergence sequences X to convergence sequences Y. Here it is sending convergence sequences in Y to convergence sequences X. That is a condition given in C. That also tells you the proof that that family of convergence sequences in X will be same as family of convergence sequences in Y rho. Not only that, that means Xn will go to X with respect to this metric D if and only if xn goes to x with respect to this shows the metric respect to metric 4. Then they are equivalent. These are the equivalent conditions. Okay, so can do that. Famous thing is that why so any one of them usually we write that first we write these are equivalent, then I say any one of the conditions. Okay, so particularly if they generate the same topology, same family of open sets. Now look, the famous thing is that the well-known things rather, if you start with a metric D, then this will I have taken rho xy that in the beginning I said this gives you another metric. This this is first of all this is a metric on X. Second of all, D and rho and equivalent are equivalent. But the good thing about it is that rho is a bounded metric. That means any metric is equivalent to a bounded metric. Okay. Example 2 is not wrong, but what I wanted to convey that is not there. Now let me tell you something. This is complete. Now look, the standard metric here, the usual metric. Why I am taking this will be clear. So this is not complete. This is very important. Okay, like 0, 1, the way you proved that's the same way you can prove that. Here you can minus pi by 2 plus 1 by n, you can take a sequence so that it will converge to minus pi by 2, but that is not here. Similarly for pi by 2, it is not complete. But if I take a function, look here. Here actually it is the function arctan, tan inverse x going to tan inverse x. So that now on this you give a new metric. What I'm saying, now don't confuse with that. Okay, you can take y1, y2. Suppose y1, y2 if you take, the standard metric will be this usual metric, but that is not complete. But now if I give this on this metric, I give look d y1. Here I have written row actually. Look, if I give this, look, I am not giving y1 minus y2. I am taking the angle. Okay. Well, sorry. The angle y1 y2. Wait a mistake. That mistake I did an example too, but it is still working. It will be a metric. But what I want, I can give this metric. I can give this metric. Wait a minute here. This is the row I have written. Fine. This is G. Write this because when I'm taking from here, they are angle actually. So tan y1 is tan y2. Okay, right. So that you should check these are two metrics. Now look at the metric D here. First, you should check that T so that your set is this, but here you are not giving the usual distance metric. You are picking up y1, y2 here, and you are giving this metric. Okay. Now check that it is complete. You should check it is complete or not. Okay. Now look, if this is D is complete, also check D and are equivalent. This check one. This is complete. But look, this if it is true, D is complete coming. You're working on this. This is it is actually complete, and this is not complete. Not complete means here. That means, look, you have two equivalent metrics. One is complete, one is not complete. So it is possible that if you have two equivalent metrics with respect to one metric, this is complete. With respect to another metric, it is not complete. Okay. Look, minus pi by 2 instead of this, I could take this open interval 0, 1. I will just shift to by another map. Okay. I could take that. The reason is, look, in the definition and the result I am getting, collection of convergent sequences are same. But the thing is that completeness related to Cauchy sequences. I am not saying when I am defining equivalent matrix that collection of Cauchy sequences, first of all, collection of Cauchy sequences is same as the collection of Cauchy sequences with respect to the both metrics. That means collection of Cauchy sequences. That's why you should write now basically when you are considering two metrics, that means you should write D Cauchy and rho Cauchy. That means for two metrics. Here D Cauchy, you are this Cauchy. Here. That means Cauchy with respect to this metric, Cauchy with respect to this metric. I have not said anything in the while defining equivalent metrics that they will have the same collection of Cauchy sequences. That's why it is happening. So I have written 1/3 page of the comments in page 123 that you should look that. So I said that we have note that in the definition of equivalent matrix, we have only talked about the family of convergent sequences with the same limit. If you want to get rid of this anomaly, then you need to a stronger definition of the equivalent matrix, because collection of Cauchy sequences may be the much bigger than collection of convergent sequences. So that if you want the same collection, then actually you need to define uniformly equivalent. Look, how will you define uniformly equivalent? Previously, equivalent conditions, I gave the one condition that these identity map. That's the importance of another importance of uniformly continuous map. Both are identity maps. Look. So if they are equivalent, if and only if these identity maps are continuous. Okay. Now we define if they are uniformly continuous, if they are uniformly continuous, both directions, then we say that uniformly equivalent. Then you can say, you can easily prove that, because you should know uniformly continuous sends the Cauchy sequences to Cauchy sequences. So that if this is identity, it is uniformly continuous. So Cauchy sequences here will go to Cauchy sequences here. Similarly, if you assume this is uniformly continuous, Cauchy sequences here will go to Cauchy sequences here. So that means collection of Cauchy sequences in both XD. Sorry, this should be X go. I am taking Y. This is the same thing. Then set X. Okay. If they are uniformly continuous, these identity maps, then this is called uniformly equivalent. Uniformly equivalent. And in this case, it will be complete. The collection of Cauchy sequences will be same, and so that also it can be proved that X2 will be complete if and only if in this case. I'm not saying it has to be complete, but this I can prove. X2 is complete if and only if X row is complete. Okay. That exactly the result I showed. I put as an exercise. D and row to uniformly equivalent matrix on a non-empty set X, then D is complete if and only if row is complete. Okay. I have given an exercise that if it's Saint Cauchy, look here. I have proved that before, and so you can see that uniformly continuous functions sends Cauchy sequences Cauchy sequence. But converse need not be true. But you can prove that this thing, that is the exercise, last exercise I have given. That suppose a map F sends Cauchy sequence basically in X, in XG, Cauchy sequence in Y row. This need not be uniformly continuous. That you should find a counterexample. But you can prove if you have this, then F has to be continuous. Well, you can try to prove yourself, or you can look that in Ali Pranthis Barkinsa Kitab that I said that theorems 6.19 page 45. Here they are using even odd arguments. That how will you prove that? Even odd arguments means suppose you have two sequences in a metric space. Then I construct another sequence Zn. Okay, how I do that? Zn equal to, you can take that Xn if n is odd. You could do the other way also. On Yn if n is even. That means you put, okay, actually, yeah, this is something, let me write it. N is odd. So how will you do that? Actually, I think something writing wrong. Let me write that. Z2n, right? Take Z2n equal to Yn. Okay, this thing. And Z2n plus 1, right? X. This is correct. So even when you are taking yn and odd, you are taking this. Basically, you are doing what? Look, n equal to 1, this is coming z3. Okay, z3. N equal to 1, z2. z1 you can take anything if you want. In fact, xn here is 3. So that, let me see that what we are coming in. N equal to 1, that is z2. z2, look, wait a minute. Let's see that. z2 is y1. z3, actually, okay, fine. You take this, not exactly this. Wait a minute. Right? 2n minus, not 2n plus. Okay. So that when you take n equal to 1, okay, then it will be z1. So this is this. So this you are doing. समझ गया? Alternatively, you could interchange the role of x and y and y1. Okay. Then you should look at what will be the convergence of Zn. How does it depend on convergence? Its convergence. How it depends on the convergence of xn and yn. If you first figure out, then it will be easy to do the exercise. Okay. So that I have taught two things: uniformly equivalent, equivalent. Now I am going to topology. But this is very important. Particularly, you should look at this thing, that what I discussed. Here you have the usual distance metric, and you have another metric in terms of the tan. These two metrics. Think of that. Okay. Now I am giving you the basic topological concept. I am not going to into detail on that. That I will do next semester. So I have written the topology basics. Okay. This is related to equivalent matrix. Look, I have done the two matrices you have. And I say they are equivalent if they generate same open set. That means tau rho is same as tau d. Now look, from now onwards we will do same many properties just relating given by the open sets. I do not need to bother which metric is giving, d or rho. Okay, so that they are actually properties determined by the open sets, not directly by the row. But you may say, argue that okay, anyway, I am getting my open sets by a metric from a metric. That is fine. But different metrics can give you the same family of open sets. Okay, that also I need to know whether my choosing of metric really really affects some property. Okay, so thing is that, and in topology actually we start with the open sets actually. Then also in NL, how do I define open sets? Because here open sets I defined from a metric D. Okay, fine. So that first, while defining open sets, I need to get rid of this. Look, xt, we are getting open sets, and then you are getting some properties related to that. The scheme is this. Thing is that if my property is entirely dependent on open sets, look, while I deal with open sets, what I am using. Question is that am I using D directly or not? Or I am using the properties open set. Look, what is the properties open sets? The properties sets we have three things. One, X and phi are open. It's a D open. Fine. Two, arbitrary union. That means any union of open sets is open, and any finite intersection, finite, which is same as take intersection of two sets. By induction, you can take finite. Any finite intersection of open sets is okay. And I am saying from properties. Suppose I have a family of sets. That means this is called, I'm writing tau. Okay. So tau is a subset of power set of X. That means tau is a family of subsets of X. Is a family. Tau a family of sets, subsets of X. And suppose that family tau satisfies these three things. That means X and phi are in tau. Any union of members of tau again is in tau. And any finite intersection of members of tau is again in tau. Suppose don't use the term open now, please, because open is just giving you the characterization of how you are defining the family. So suppose you have a family of subsets of X satisfying that X and phi are in tau. Any union of members of tau is again in tau. Any finite intersection of members of tau again in tau. Look, why I'm doing this? Suppose you have it, then many things what you have proved here, I'm just by using, I can prove those properties. I don't need any D. Okay. So that means I don't need to use D. And there the idea of the topology comes. D gives a particular topology. From D we get open set, but it is not necessary, required. Often that will do that. Later on I'm teaching compactness, connectedness, all things depend on only this thing. That means what I'm doing, suppose we have X non-empty set, of course, non-empty set, and you are considering power set of X, and tau is a subset of course, tau is also non-empty. That we'll see that. That means tau is a non-empty family of subsets. Some subsets, not necessarily all subsets. Non-empty family of subsets of X, such that now I'm putting the condition. 1, X and phi are in tau. It's a Greek letter. 2, whenever, if this is an arbitrary family, this R is an index set, so they are in a tau. Okay, the subset of tau. Okay, that means each of them, that is each y belongs to tau. Okay, then the union, that exactly after getting the definition of open sets in a metric space we have got belongs to tau. Here in the notes I have put only two intersections, but that is same as finite intersection because of the induction. So UV, I said if UV belongs to tau, then U intersection V belongs to tau. By induction, it is the same thing. Suppose U1, U2, U1 you take. Okay, then U1 intersection U2 by this belongs to tau. Of course, if you have finite intersection, this will be true. And if this you have to do, then with this you take U3. This is belongs to tau, this is belongs to tau. By that, this belongs to tau. So by induction, you can see that. So it's the same thing if you take finite. So that, suppose I have this. So that means starting from metric space, you are getting this. But now I am only looking at this part. I am not looking at the metric. वो पीछे है, ठीक है? I am not bothered about it. Suppose you have this. Okay. Suppose you have this. I am just going to define topology today and just giving some examples on that. I am not going to do much today. Okay. So that, look here. So suppose you have it. Look what you got from it from the metric and then hello, कौन फोन किया? कौन फोन किया? हाँ? Axis Bank है, I am taking class. Please call me later. Hello. Can you hear me? Hello?
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Okay, now listen.
Yes, sir.
So tau. So that way I can define tau family. It will have to satisfy three conditions. X and phi are in tau. Any union of members, any union, finite, infinite, whatever. Members of tau again in tau. Any finite intersection of members of tau is again in tau. Then tau is called a topology. It's called a topology on X. Like the metric space, look, and this pair is called a topological space. So that if you start with a metric, that was giving me a topology, tau d that I wrote. This indicates this topology is coming from this metric. So that way, this is a topological space. Okay. Right. So this is called topological space. Look, topological space, you need to take a pair. Often we say let X be a topological space, but that means we are considering this a topology on this. Okay, so only X is a set actually. To be precise, you should, like metric space, you should give a couplet pair X tau. Okay, then you can now of course you can have a legitimate question why you need to consider, is there, first of all, of course you can ask, is there any topological space? That means topology which doesn't come from a metric. Answer that question. First thing, is there, given any set X, of course non-empty, is there any topology tau on X which doesn't come from a metric? Wait a minute. It doesn't come from a metric. Okay, this thing. Because if a topology always comes from a metric, then of course you should not bother about it. A good mathematician, and they are not the mad people. They are highly reasonable and rational people. So you should understand, if there is not a topology which doesn't come from a metric, then of course I won't consider topological space. I will be happy with the metric space. At the same time, I will show that of course there are many topologies which do not come from metric, but still metric space has its own role, because later on you will see that as you proceed with the topology, that a metric space among the topological spaces is probably the nicest topological space. A metric space is a topological space, and metric space is probably, I'm writing probably, the nicest topological space. If you do not agree with that nicest topological space, you can at least say this is a very nice topological space. Later on you see that. Okay. ये दो ई क्यों लिखा मैंने, एक ही आएगा. Well, first thing, let us see that two examples. We have x, non-empty set. Now my first condition, x and 5 should be there. So if I just take this, that has to be there. That is minimum condition. But if I take this, this will give you a topology. Because you need to take union, union will be, if x 5, either will be x or 5, intersection will be also x and 5, that is there. So tau is a topology on x. Look, this is the smallest topology on x. What is it? Because if you take any other topology, that has to be, this one has to be contained in that. Because ultimately you should know that. This is this. So if you have two topology, tau 1, tau 2, so there is a subset of px. So I can compare if it is possible. It is possible that tau, whether it is this. Not be that given a two subsets of x, they need not be comparable. A may not be contained in B, B may not be, but that is also may be true. So one of them. If you have one of them, then it is called the two topologies are comparable. Comparable. In this case, tau 2 is called a stronger topology than tau 1. And here it is tau 1 is called stronger than tau 2. Or other way you can say tau 1 is weaker than tau 2. Similarly, you can use strictly weaker if you have this subset but not equal. Then it is strictly weaker than tau 2. Tau 1 is strictly weaker than tau 2. Or tau 2 is strictly stronger than tau 1. Okay. Stronger than tau 1. Now look, this is that says is the smallest topology because this is the minimum condition I need. So that way it is the smallest topology, because if you have any other topology, tau 2, then it has to be this one. This has to be contained in this, because tau 2 at least will have this. So this is a topology. Similarly, if you take tau 2, now if you take tau 2 equal to the whole thing you are taking, power set of x. Look here, there is nothing to prove because everything you are working inside it. So here everything I have given you. So this is the topology, and this is the largest topology because ultimately it has to be a subset of this. So this is the largest topology. This topology has got a name. This is called trivial topology or indiscrete topology, because trivial topology, and this is called the discrete topology, because in metric space, you remember that from the discrete metric space you got a topology, every subset is open. That means you are getting discrete topology. That's why it is called discrete topology. And it is called trivial topology since it is opposite. It is the largest, this is the smallest. This is also called indiscrete topology. Indiscrete topology. Okay, right. Discrete topology, indiscrete topology. Later on, while starting with topological spaces, you see discrete topology, I already told you, while starting metric space, it's a good friend, at least for counter example. Similarly, it's also good friend for counter example. Indiscrete topology. Okay, now listen to me. That I am saying this topology can never be generated by a metric tree. It can't come from a metric. That exactly I was telling you. I need first an example. Though you say it's a very trivial example, fine. But still I have an example. Later on we'll see many examples. That this cannot come from a metric. Why it cannot come from a metric? Okay. Reason is, now look. Remember that if you have a metric space Xt, then we have proved that every singleton, if x belongs to x, then this is closed in Xt. There I defined closed. Here also I defined closed. Same way. But that means you have proved this is open. This is open. In Xt. Okay. Now you see that here. Suppose you have this. Tau is trivial topology. And also assume X has more than one point that you need. Look, if X has only one point, there will be only one topology, trivial topology. Understand? So more than one point. X has more than one point. Okay. Now look, if I take, that means it has at least got xy in X. Okay. Now look this. If it comes from a metric, open set will be the same thing. If it comes from a metric, this should be open. But look, I have only open set X and phi. But this is not phi because y is here. So this is not phi. In fact, X is there also there. So I have taken that. But here y is there. Okay, this is not phi. Okay. Also, look, this is not phi, and of course this is not whole X because X is not here or X is here, small x. So this is not phi, this is not X. But only open sets I have X and phi. That means this is not open. That means this is not open. In trivial topology, this you need more than one point because I need at least 2 points to have my arguments. Okay. So look, here y belongs here. That means this is not phi, and X doesn't belong here. That means it's not equal to X. But if it came from metric, this should be an open set. But it is not open set because members of tau are called open sets. Actually, more precisely tau open sets, because we are doing members of tau are called tau open set, or simply we say open set if we do not have any confusion with tau. So trivial topology can never come from a metric. Okay. In fact, there is a term, metrizable topology. What it means then? Metrizable topology means if your topology, that means tau, if tau comes from a metric, then it is called a metrizable topology. Okay. On the other hand, if I take discrete, this is a metrizable topology because it gives, if you choose discrete metric D on this, I am using the same notation, but you should know tau, no notation. This means the topology generated by tau will be same as this thing here, this tau. Okay, tau is used for topology. Okay, so that this is a metrizable topology. So that there are many topologies, you will see that as we proceed. Well, see then why I should study general topological space, because there are many nice spaces come. They are not metric spaces, but still they are good as topological spaces, and we need to study them. Okay, right. I was telling you that different types of topology. Last time I gave the areas and that many of them do not deal with metric spaces, but they are still deal with some nice topological spaces. Okay, so that, well, and here again I should remind that page 125 definition, that closed set like the metric space. Look, whatever ultimately I am getting in metric space in terms of open set, that I should have here. You should know the philosophically. The mathematicians are not mad people. If you have something old and good that you preserve, that you don't destroy while discovering something new things, while trying to define some new things. If something old and good, okay, old and good, that to preserve it while going for a new thing. But if it is not good, then it's better in your life you discard it. Okay. But old and good, if you preserve it, there will be a so-called continuation in the civilization. That is we call in Sanskrit parampara. If it is bad, old, don't think, oh, this is old, it's classical, so I should don't go by that. You should discard it. That means particularly if you have some prejudice or bias, you should get rid of this. Well, I'm just a little bit going out in the sense that, first of all, before becoming a mathematician or whatever, becoming a teacher and that, you should be a good human being. Good human being. This has the philosophy with the mathematicians. And as a good human being, you should not have this prejudice and bias. Okay, you should get rid of that. Okay, so similarly, here in mathematics, if something old is not working or something inadequate, usually mathematics are, of course, they're old and good things are there, but they're sometimes it's called adequate and inadequate. But the mathematics is a good thing that from inadequate we think of, we generate the adequate things. Adequate things like here from metric space. In fact, later on in the universe of all topology and that, you see metric space is not enough, so it is inadequate. From that we have got the idea of the topology. So that topology makes it adequate. Okay. The human philosophy is that also, that if something is inadequate, it may be good, but you should make sure that I should make it adequate. Okay, right? So that topology in that sense is that thing. In fact, in major theory, next semester you'll do. In BSc you did Riemann integral. Riemann was a very good mathematician, one of the brightest mathematician in the history of mathematics. But the point is that later on it turned out that his integration is not enough, adequate. He is inadequate. That's why the Lebesgue integration came. But still the contribution of Riemann is there, because he could first think of the idea of the integration. But it was later it turned out to be inadequate. So Lebesgue came to make it adequate, the Lebesgue integration. Similarly, the parallel idea is that metric space is very nice, but often it is inadequate. So we want to make something adequate. So that's the idea. Now the thing is, in metric space you have defined a closed set, same way you define. Now you have this collection open sets. So you said A subset of X, then A is called closed. If more precisely it should be called tau closed, because everything with reference to tau. If X minus A belongs to tau, that means if X minus A is open. Here open means members of tau, or more precisely tau open. Again, you on a topological space you can have more than one topology. So if you consider more than one topology at a time, then it should be clear whether it is tau open, sigma open. But when you consider only one topology at a time, then you can simply say it is open set. Okay. So like proposition 3.1, look, I have defined open sets. So that's the way, the family, so that I do not have the result of open set, but I have the result on closed set. So the way he proved in metric space by using De Morgan's law, proposition 3.1. Look, X and phi are open, so X and phi will be closed. And there, by De Morgan's law, you are using that only finite union of closed sets will be closed. But arbitrary intersection of closed sets will be closed. Again, between open and closed, I told you that open and closed, any result, if you have it, open, closed, arbitrary, and finite. This word, union, intersection. Okay. This is, don't touch that here. But I am saying if you replace any result, again remember that you replace open by closed, but don't be selective. Closed by open, union by intersection, intersection by union, you'll get another result because of De Morgan's result. So proposition 3.1 is valid in there. Okay, that example one I have given you that is called the trivial topology. Okay, discrete topology. Okay, right now I have given definition 3.4 metrizable topology. Look here, I said if your topology comes from a metric D, then it's called a metrizable topology. Like trivial topology, if you have x more than 1 point, it is not metrizable. But if it is metrizable, then you can ask the question whether that topology comes from a complete metric. It may or may not. If it comes from a complete metric, then it is called completely metrizable. Okay. In fact, discrete metric is a complete metric trivial. So this is completely metrizable. Okay. So that your topology, if it comes from a metric, then it is called metrizable. If it comes from a complete metric, then it is called completely metrizable. Okay. So that example I have given. Now, here, let me give you the examples of that, more examples. That, just see that. Before that, example 6 you go. I have taken x equal to r. Okay, and tau we are giving this. This thing you need the whole set and the empty set, and Q you are taking set of rationals and its complement P. This will give you a topology. You can easily check that it is a topology. Of course, it is bigger than trivial topology and smaller than discrete topology. But you can see that this is not comparable to R. You have this topology given by this metric, metrizable topology. This is not comparable to this topology. In fact, these are open here, but these are not open here, Q and P. So this is not metrizable. In fact, topology generated by this is not this, you should prove. And this is also true, is not this. This is, though I am using the same letter, it means the topology generated by this metric. They are not. That means they are not comparable. Okay. Here, show that QP are open here, but they are not here. Similarly, here you can see that this is open here, but this is not here. Okay, so that you may have two topologies which are not comparable to each other. Okay, right. Now the thing is here, well, look, this idea in NAL I could take in on any set, non-empty set. Suppose you have X, you have A subset of X. It may be empty also. Then if you take this X, phi, A, X minus Z. This will be a topology. Well, if you take A equal to phi, then actually it will come only trivial topology. If you equal, and if you take A equal to X, that will be also trivial topology. So that it doesn't make a difference. So that you can take K now empty also, but it will give you a topology in YAL. What example 6 I was giving, the YAL thing, it is a topology. On X. Now the two things are very important that I want to define. Okay, so let's read it. I am coming back in 10 minutes. That read about the topology by that then and that. Try to understand. I will define co-finite topology and co-countable topology. Okay, I will be back in 10 minutes.
দুটো ক্লাস করে কোনো ক্লাসই করে
Hello, let's start. Hello? Hello?
Yes,
Yes,
sir.
sir. Yes, sir.
Can you hear me?
Yes, sir.
Hello?
Yes, sir.
Yes, sir.
Hello?
Yes, sir.
Yes, sir. Yes, sir.
Hello?
Yes, sir. We can hear you.
Can you hear me?
Yes,
Yes,
sir.
Yes,
sir.
Yes, sir.
Okay, let me start on that. Okay. Anyway, while teaching topology, I should remind you something that if you feel comfortable in this course, whatever I am teaching in the exam also you can answer for metric space. Okay. Even if I give it some topological space, you can start with a metric space. It's not a problem. Okay. But next semester you should remember that you'll have the course in topology. Okay. But point is that later on some cases you will see that if you prove it for the general topological space, it will be easier than metric space. It sounds strange, but it's true. Okay. Sometimes general thing, proof for general thing is becomes easier than the special case. Okay. Now here, I want to discuss these two things: cofinite topology and co-countable topology. Actually, here also I have written that actually co-finite, this is a hyphen, so co-countable. These two topologies. Okay. What is stands for co? Co actually stands for complement. That's why some people prefer to use hyphen. So example 4. Example 4 and co-countable topology, the idea is similar. The ideas are similar. So that better you try to understand this thing. It's a very simple thing. So example 4 is page 127 actually. Okay. So that here you have a non-empty set. Of course, when you do topology, always you start with a non-empty set. Okay, you don't try to define topology on empty set, and that doesn't make sense. Okay, now tau, of course, this is minimum thing I require. So you have this and a subset of x that I'm giving such that its complement x minus a is finite. Okay, that's why the co stands for complement. Here I am defining open set other than x and phi. Okay, we are taking that its complement is finite. Okay, so this will give you a topology, and that is called the cofinite topology. It's very simple. The other than x and phi open sets will have to come be there. So I am writing separately plus this. But you can see that if x is finite, if x is finite, because I didn't say whether it is finite or infinite, then any subset of x will be, because any subset of a given this, that its complement will be also finite, that will open. In that case, tau will be a discrete topology. That means any subset will be open. Okay. Got it? Now, here, so that when actually we consider cofinite topology, then actually we take x is infinite. Because for finite x, it will be discrete topology. So that when you consider cofinite topology, usually we take x to be infinite. So that topology won't be discrete. You can see that. Then topology is not discrete. You should check that. If x is infinite, then topology is not discrete. Okay. Now, look here, closed sets are defined complement. So that what will be the, so x tau, take x infinite, because for finite you know it is discrete topology. X infinite and tau cofinite topology. Now, what would be the closed sets? When it has been tau closed sets. Since I am taking the topology, I am calling it tau closed sets. What will be the tau closed set? Of course, x and phi will be there. Now look, it will be the complement of the open sets. So x and phi are complement I have taken, but other things you leak. Oh, what is open set? A subset of x such that x minus a is finite. This is open set. Fine. Now take B. If you want to make it closed, this is there already. I don't need this. So x minus b is open. If x minus b equal to either x and phi, it is done. So next possibility is that if it is open, so x minus b is finite. Which is b. That means b has to be finite. That means closed sets will be this and all finite subsets of x. These are the closed sets. Okay. X, phi, all finite subsets of x. Look, I am putting x is infinite. That I am writing separately. Okay. So the closed sets will be precisely this. I am answering the question. I have put a question here. What are the closed sets in the cofinite topology? Cofinite topology, other than x and phi, all finite subsets of x. Now look, every singleton is a closed set here. Okay, every singleton is a closed set here because all finite is a finite. Here is a definition. Let me write this because later on one result I forgot to give you that. I have written that. I will tell you that. Now you can have different types of topological spaces. Now look, so the definition one, a topological space x tau, not very sure whether I have defined it, is called T1 or is called a T1 space or a T1 space if every singleton in X is closed in X. That is, X minus X is open here. That belongs to tau for all X belongs to X. समझ गया? This is called a T1 space. Actually, these are called separation actions. Why it is called T1 is later on you will see you have T2, T3, T4. I will talk about T4 only. There are T5 also. So x minus x and that. Okay. So that means what you are getting? That if cofinite topology, that means actually often we say that this topology is T1 topology because ultimately when you define T1 space, you basically define in terms of the topology. So often we also say that tau is a T1 topology. So cofinite topology, what I proved, cofinite topology is a T1 topology. Look, finite union of closed set is closed. So if a singleton is closed, then a finite set will have to be closed also. Okay, cofinite topology is a T1 topology. Now, here I should give you the one definition on that. Suppose, okay, that I will come later on. Okay. Now, co-countable topology. Look here, put this word here. Look, whenever I was defining cofinite topology, so it is a rather battle between finite and infinite set, right? So that when you have co-countable topology, it should be a battle between countable and uncountable. Actually, it should be. Okay, right. Now, let me define formally. So X is a non-empty set. Here I have used the word at most countable, but some people also just use countable. At most countable means the meaning. Some people use the word simply countable also. It means either finite or if it is infinite, countably infinite. That means it can be put into one-to-one correspondence with a set of naturals, countably infinite. So that is called at most countable. Some people just use the word countable. Here, this topology, co-countable topology, I am defining. That tau, like before, anyway, you'll have to include that x and phi union a subset of x such that x minus a is at most countable. ठीक है? This is the open sets. This you can check. This is the topology. Okay, and again you can check if x is countable. That means x is at most countable, or particularly if you take countable infinite. If x is countably infinite, because x minus a, if x is itself countably infinite, then x minus a will be also at most countable. Then x is countably infinite, then tau is discrete topology. Like cofinite you are doing. So that when co-countable topology we take usually x uncountable. If x is uncountable, in fact, if and only if you can prove that tau is discrete topology if and only if x is countably infinite. You can prove the other way. Similarly, here also you can prove that though I am writing, if x is uncountable, then tau is not discrete. Okay. Again, now look, what will be this co-countable topology, and what will be the closed sets here? Closed sets, tau closed sets. It will be x, phi, that will be always there, union, complement, like the way I argued with cofinite sets. All at most countable subsets. Subsets of x. All finite subsets of this, here all at most countable subsets of this is co-countable topology. So particularly finite subsets are also closed. So singleton is closed. So this is the T1 topology. That means T1 space. This is T1 topology. Okay, got it? This is example 4 and 5. Next semester will also need. So example 4 and 5 read. This is a very simple thing, but they are good friends. Okay. Now, so up to this much this is fine. Now I will just cover 1 or 2 pages of that. Now let's see that. Now the thing is that for further idea, how to go that? Like, look here, I told you that you don't destroy the old good old things. So point is that other ideas like, look, what are the ideas there in the first page I said that I have not, I went straight to the open sets. So I have not defined interior points. So this is there. How will I define it? How will I define closure point? How will I define boundary point? And how will I define accumulation point? All these points. How will I define? That's the thing. Look, I should define such a way that when I consider metric space, that will be the same thing. That has to be, it can't be different. Can't be different. Okay, because I am trying to generalize the ideas of metric space. I am not destroying metric space. So it can't be different. So that I'll have to define such a way that when I consider a topological space is metrizable, it will be the same thing. But before all these things also, how will I define neighborhood of a point? Look, neighborhood of a point in a metric space I have defined this way in terms of the ball. But ball is not here. Okay. So how to get rid of the ball? Such a way when I go back to a metric space, I will still have this thing. Okay. So that's why. Okay, here I explained that in page 127. Now we'll have to define the other notions of topology in terms of neighborhoods of points. In case of a metric space, we have that I said that. But in topological space, we do not have access to a distance. So how to get rid of this liability of distance? Basically, while doing topology, you need to get rid of the distance metric. Okay. But when you give me metric, it will be the same thing. Now look, the first result in topological space, how I saw that neighborhood of metric space, how it can be redefined rather in terms of equivalent conditions, in terms of the open sets. Look, the result on page 128. That's the way the idea I am giving you that. Look at the result. So suppose you have this thing and x belongs to x. Then and U is open, suppose, which contains x, rather not that I am saying U open, then U open, then and x belongs to, then what I get, x is a point here, then shit. Oh, I see. I didn't realize. Now look, here I get that x belongs to U if and only if, look, U is open given and x is any point, if and only if there exists, because U is open, if x belongs to, it has to be an interior point, there exist R greater than 0 such that fine. Okay, you can easily prove that because if x belongs to U, then U is open, it's an interior point, you have this, and obviously x belongs to this, other way it is trivial, x belongs here, so x belongs to U. Okay, now the thing is, so for a neighborhood I have defined this. Got it? Got the point? For a neighborhood of x in a metric space I have it. Now I have this equivalent. So that how will I define a neighborhood in topology? Well, I will simply define any open set containing x is a neighborhood of x. Any open set containing x is a neighborhood of x, because then I will have this also. So that will be consistent with the idea of the metric space that exactly I defined. Definition 3.5. Let x now be a topological space x belongs to x. Then any open set containing x is called a neighborhood of x. Okay, that exactly. U is called neighborhood of x if U is open and x belongs to U. This is definition. But this way, look, any point of, if you take any other point y, then u is also neighborhood of this point. That also happens here. Okay, so that note that u is actually a neighborhood for all of its points. Okay, right. Now once I have got the neighborhood, then I can define interior point. But again, look at what you got, the result in the metric space. Okay, in the metric space you got, then x is an interior point of this if and only if there exists an open set such that, now look, interior point, if you have this xt metric space, you got the result. Again, another result I am saying is a subset of x. You can take, of course, non-empty. Then if I say x is an interior point, I got what? If there exists an r greater than 0 such that but this happens, x belongs to AR. It happens that I told you if and only there exists an open set, that so that open set I will push here. So in topology, when you are having topology, you have topology, I will replace it by the neighborhood of A. X tau, x belongs to A is called an interior point of A if there exists, I will replace by the neighborhood U, that is an open set containing x such that exactly, look, I am replacing by U. I am replacing this by U. Not only that, I am replacing the distance. You need to get rid of distance such a way when you go back to metric space, get the same thing. That exactly I got. That's the way interior point. Now the interior means the collection of all interior points. That I said that interior of P. Okay, that is a collection of all interior points of this. Okay, now exercise 1 you can do that. That A is open if and only if interior of A equal to this. Okay, so this is the idea that I have given you usually the books that do not write it. Okay, and exercise 2 I have given you that you should do it. Again, look at that closure point, accumulation point. I have given the result here. Then in metric space, I will do that. Look again. Now closure point. Closure point. Look there. I got what? Xt metric space. X belongs to X, and A is a subset of X. I said, look, X belongs to A bar if B XR intersection A not equal to 5 for all r greater than 0. This is for all r. Then this is the neighborhood of x there. So here I should have for all neighborhood of x. That means if you have topological space, that's the result in the A part A, page 129. Look. So that it should be that this way what? X belongs to A bar if U intersection A not equal to 5 for every, that is all, every neighborhood of X, every neighborhood U of X in X tau rather. This, if you want to, when you consider more than one topology, then we make a distinction like tau neighborhood, tau open. But here I am just considering one topology, so I can write every neighborhood. For every neighborhood, Okay, look, the way, that's why you need to study metric space well. You need to understand the concept of metric space well. Okay, so every neighborhood, but on the accumulation point, what you got? Accumulation point you omitted A, right? So that you had this. So I should have, to have this, This is same as this. That I explained that in two sets. These are same thing. Okay. So that you have this. For every neighborhood, if you have this, then it's called an accumulation point. Okay. Then you can have in a metric space result. Now I am defining definition 3.7. You see that X is called a closure point, accumulation point. The set of all closure points called A bar, set of all accumulation points A prime. Okay, and X is called a boundary point if it belongs to the closure of A and as well as the closure of its complement. So definition of 3.7, after you do the result, then it automatically comes that this way. Here I will teach you tomorrow. I will take the class in the same time. Okay, now I am going to finish it. So all these definitions is come. Only thing I would like to tell you that you should do that. I have given the exercise theorem 3.2. Page 130. In C, because it's true for metric space, I said prove that A prime is a closed set. Here, this A prime derived set, the collection of all accumulation points. Here you assume we need that was not there. Okay, my TA last year he pointed out need X to be T1. Reason is very simple. Look, U minus X when it is T1, if U is open and X, if X is T1, then U minus X will be also open. Because reason is U minus X is, look, this is simply U intersection. If singleton is open, then this is open, U is open, intersection of two open set is open, so this is open. Because this you need for these accumulation points. So in C, you assume X to be T1. Particularly, it will be true for cofinite topology, co-countable topology. But look at that. What about trivial topology, or if it is not T1? In fact, many things are not only trivial topology. Look here, when I give you this thing, R, phi, Q. This is also not T1, this topology. This topology also not T1. Okay, and here you can see, check that this need not be true. C need not be true here. So that in C, you assume that. Okay, so that I will recall the definition of closure point, accumulation point, everything tomorrow. Okay, but this is the beginning. This is the thing you need to know all this about topology if you want to handle topology. Okay, but again I am telling you, if you don't feel comfortable in my questions and that, you can assume this metric space, though it won't give any extra advantage. That much also I can tell you that. Because ultimately, the questions I will give, if it is not a metric space, you'll have to, you all need open sets. But if you feel comfortable, you can assume them to be metric spaces. Okay, I will meet you tomorrow at 11:55. Okay, I will send you the invitation. Bye.
Okay, sir. Thank you.